Okay, hi everyone. Welcome to the Native Code and Gradle talk. So I just want to give an overview of the support for C and C++ development in Gradle, basically high-level overview of the concepts. And a lot of these concepts apply to not just C++ and native development, but to sort of Gradle 3.0 in general. So the way we're planning for software to be developed in the future is very evident in the way you develop software in the native space now. So it gives a really good insight into that. There is a workshop after lunch, so a 3-hour workshop on actually getting your hands dirty and cutting code. So if anyone So I'm going to skim right up pretty high level, and then if anyone really wants to dive in, the workshop will be after lunch. So a little bit about me. My name is Darryl DeBoer. Everyone calls me Daz. I've been working at Gradleware and now Gradle for about 4 or 5 years now. Most of the time I've been working deeply on dependency management, so that's my specialty within Gradle. But a couple of years ago we had a big push to try to basically embrace the C++ native development world, and did a lot of work to basically add capabilities to Gradle to do that. So I was pretty heavily involved in that. And now I'm leading continued development in that, as well as doing some more dependency management work as well. So there's a bunch of things that have gone into developing native code support in Gradle, and and some of them are really specific to native, and many of them are not very specific to native at all. So one thing that's fundamental is the platform Gradle itself. So we basically Gradle provides an extensible, pluggable platform for developing software. So it gives us a really powerful platform. You know, the execution engine, the daemon, all these different things are a really important part of making native code support work. Then we've added a bunch of specific features for native language support. I'll go through that pretty quickly, but that's the sort of thing you'll cover much more detail in the workshop if you go this afternoon. We have an expressive software model that we've developed partly for native code support and partly just for this vision of Gradle 3.0 that we're talking about. So I'll talk a lot about that today, or quite a bit about that today. We added support for binary variants, so the ability to build multiple outputs from a single set of sources. So not just the ability, but making it easy to do that, to make it easy to say, here, I want to build I want to build this same thing in 3 different ways, which is not something you commonly do in, say, the Java space. Toolchain support is really important to our native support, and we've added some toolchain support, and it's something we plan to expand on and make a lot richer in the future. And finally, dependency management, but not just dependency management, but sort of model aware. So we have this expressive software model. Such a fundamental part of all building software is dependency management, and we've developed dependency management that's basically deeply tied into the model that you develop. And I'll talk about that today too. That's just a high-level list of the sort of things that I'm going to try to cover today. So firstly, just like a laundry list of the native language features that we've been adding. So we call the first line here executable static libraries and shared libraries. We call these components. For lack of a better word, we're still trying to come up with a better term for that. But basically, your software model includes components, and the 2 types of components we've defined in the native space are executables and libraries. And we consider a shared library and a static library to be variants of the same thing. They're both functionality provided by an API. Executables, on the other hand, do not provide an API. They might provide a service, or they might just be something they might be an end user tool. We've added a bunch of language support. So there's 7 languages up there, I think, something like that. So so I'll talk a bit about the language support and what we needed to do to add that. We've added some toolchain support, so GCC, Clang, and Visual C++ are the 3 toolchains we support out of the box now. It's possible to add your own customizations to those, and in the future will be possible to add your own completely arbitrary tool chains. It's something we haven't quite got nailed yet, but it's something we're working on. Multiple variants with flexible configurations. So that's what I discussed before, just basically the ability to build multiple outputs from the same set of sources, build the same component in multiple ways to be used in different ways. So we added parallel incremental compilation. So the parallel compilation is something new this year. So it was a bit of a performance problem that we couldn't leverage any of the extra processes on machines because we weren't compiling in parallel. We now have fully parallelized incremental compilation, so we only compile what's changed. We've added support recently, or actually in Gradle 2.5 we'll have support for pre-compiled headers, which can be a really tricky thing to get right when you're doing software, when you're doing a large software stack, but they can make a big difference to, especially in C++, can make a really big difference to compilation time. So we've tried to make it simple and tried to make it sort of foolproof. I guess maybe not quite foolproof, but simple. But yeah, so the idea is because we have a strong model, we can actually do precompiled headers in a way that can work cross-platform, cross-toolchain. So we've got some dependency management built into the native language support so far, which is library dependencies. So basically, when you have a library that exposes an API, it means that you might have something else that depends on that API. So within a multi-project build, we have library dependencies, and integration with two different unit testing frameworks, CUnit and Google Test, as well as a sort of a foundation for adding more, and Visual Studio project generation. So we generate IDE files for Visual Studio, and not yet any other IDEs. There's a big list of the features we added for native language so far. But first now I want to just talk about the actual software model for native, and the software model in Gradle in general. So if any of you are Java developers, you're sort of familiar with apply plugin Java and apply plugin war, let's say. And effectively, by applying those plugins, you've defined what your project does. You've defined, I'm trying to build when you apply the Java plugin, you're effectively saying, I want to build a Java library from this project. It's implicit in that single application of the plugin. If you apply the Groovy plugin, you're actually saying, I want to build a Java library that has some Groovy sources. And if you apply the war plugin, you're saying, I want to use Java sources, but I don't want to build a Java library anymore. I want to build a web application. So just by that single apply plugin, you're doing a lot of you're telling Gradle a lot of stuff implicitly, and it's really hard to then say, oh, actually what I want to do is I want to build a Groovy war. Like, do you add a separate plugin there's those two things together? Or what we've decided is it's much better to actually be explicit and say, if there's one thing you say in your project, it should be what that project is trying to build. So being explicit can make a big difference. Something about being explicit and defining what you're trying to build is it's much easier to be concrete about it. It's much easier to say, I'm building a Gradle plugin. So I'm not just building a Java application that happens to be a Gradle plugin. I'm building a Gradle plugin. I'm building a native library. I'm not just building a binary that happens to have some header files and some compiled sources. I'm building a thing that Gradle can understand. So by having this explicit model, we can provide a much richer user interface. We can provide a much richer interaction, much richer way of designing and talking about what we're trying to do. So building a domain model. And that feeds into the ability for these things to be expressive. So yeah, so the software model. I guess Gradle's always provided a rich software model. Like, it's always provided a rich model of plugins and of tasks, source sets. But those are sort of things that are how you build your application. So a plugin is a thing that Gradle understands, and we have you can ask what plugins are there, and you can ask about plugins and what tasks does it produce and things like that. But it's basically Gradle providing you its own domain model. Whereas the idea behind the software model is this, for you to be able to define what your software looks like and provide a similar domain model for that, so a rich domain model. So I just want to go through a little bit of way of how you define components in the native space. So this is an example of some code that basically explicitly declares a couple of components in a native build. So you see we've got our plugins block where we're actually saying what plugins are applied. We're saying we know about native components in this build, and we know about C++, the language. So those two things together mean we can build native components with C++ sources. And then in our model, we're saying, okay, our components are a thing called hello lib that's of type native library. Ignore the spec for now, but that's basically it's a native library specification. And we have a thing called hello world exe, which is a native executable specification. So those are the two things we define in our model as the components for our build. There's nothing in this model here that says this hello world exe depends on that hello lib, but one thing that's interesting is that straight away we've decoupled the concept of the Gradle project from the concept of the things that are produced by the Gradle project. So fairly tightly intertwined in Gradle. If you're a Java developer, fairly tightly coupled to each sub-project is it produces one primary artifact. So this is the jar that this project produces. So by introducing an explicit model, we no longer have to say this project produces. We can produce 12 different artifacts out of one project. We can spread them out over multi-projects. We can start to we're basically separating out the project structure from the actual component structure that we're trying to build. So one thing is that this set of types is not fixed. There's nothing magic about this set of types. So at the moment we have added a native library spec and a native executable spec. We've also got a JVM library spec and a play application and a bunch of other types of components that you can add to your model. And obviously we don't know how to build a JVM library out of C++ sources. We haven't got that functionality built in yet, but we do know how to build these things if you've added, and they're applied by a different component plugin. The idea is that you can define your own, and this is an extensible set. So let's say we want to develop, add kernel driver support to Gradle. We want to be able to develop kernel drivers. Kernel driver spec will be a new type of component that we want to add to the model, and then that will be presented. All of the functionality. There's nothing. I guess what I want to say is there's nothing inherently that can only be done in Gradle about these types. These are all done by plugins, so it makes the model it allows Gradle to be extended in ways that we might not expect. So one of the things we wanted to be able to do in the native domain is make it really easy to add support for new languages. So these are I guess I showed the list before across the top of the screen. Now this is the list of language plugins we have now. IDL actually is not there. But the idea is that each of these plugins adds two different things. It defines a type of source, so a source set that can hold so it can say something about the sources. So say Objective-C sources have header files. That's something it might say. So it provides an Objective-C source set that actually says, I actually have header files and I have sources. Whereas an assembler source set does not have header files, it just has sources. So there's things, so basically it defines that, and it defines a transformation of those sources into some sort of intermediate format, which is an object file. So basically that's what a language plugin doesn't know about native components necessarily. And it doesn't know about doesn't know too much about the Gradle model. What it needs to know is, okay, I know that I need to define a type of source set. So there's a base class. I need to add a subclass of that with my own customizations, and I need to know how to take one of those and transform it into object files, and put those object files in a certain place. So that's the set of languages we've supported so far. I just talked about the language source sets that get added. So I want to show, here's an example of language source sets added by the CPP plugin. So Here I've defined a native executable spec. So I'm saying, here's my hello native executable. It has a container of sources, of source sets, I guess I should say. It's a container named sources that contains source sets. This is the implicitly defined CPP source set that's applied by the combination of having a native component and that language. We automatically define, or by convention, we define a C++ source set called CPP. And you can configure the source directory, and you can figure where the headers come from. And you can also add additional source sets. So you might want to say, actually, I have some shared sources that I share between a bunch of components. I can configure that in the same way I could add the configure where those sources are located. So the default one is this is the conventional one. We only have to reference it by name because it's already been created. This one we reference it and give it a type because we're actually saying I'm creating this particular source set at this point. So once we have source sets, we can have dependencies between source sets. So because a source set can have exported headers, and that means that another source set might want to use might need those headers when it's compiling. So here's an example of dependencies between two source sets within the same component. So we've got a native executable the same. We have our sources container with two source sets, CPP and shared. Now shared is a CPP source set. It's got some exported headers. This source set saying, I depend on the CPP source set. And effectively what Gradle does then, okay, well, what does it mean to depend on a C++ source set? It means I grab the headers from here when I compile the sources from this guy. Pretty straightforward. Object files are generated. They all end up bundled up into one executable. And we can take that a little bit further to the to library dependencies. So in a very similar way to source set dependencies, where we said, okay, this source set has exported headers, and those exported headers can be depended on by another source set. A library exports an API, which are the exported headers of all of its source sets. So I can say I depend on, my executable actually is depending on this library. Library's named hello-lib. That's within, there's no project qualifier, so it must be within the same project. So it goes up there. I can also depend on a library defined in another project. So I'm saying I define on. So effectively what that means is it's a project dependent. It's basically saying at compile time, I need the headers of this guy, and at runtime, I need an implementation of this guy. So when we create an install image of this hello executable, when we actually want to run it, we actually need to build this thing and build this thing against that, and then bundle them together to run them. And I'll show a demo of that in just a sec, pretty much now, I think. So yeah, so one thing about the software model that's different to what we've done in the past in Gradle is we focus a lot on what we're trying to do as opposed to what we want to build rather than how we want it to be built. So we don't spend as much time configuring tasks. We don't spend as much time scripting actions. We focus more on what we're trying to build, what we want Gradle to build. And the benefit of this is it allows Gradle to make lots of optimizations about how do I build that. So if you tell a build tool how to build something, then you're effectively saying this is exactly how I need it to be built. But if you say, I just want one of these, I just want a hello shared library compiled with those C sources with these attributes, Gradle can go, cool, I've actually got one of those I built earlier, or I know how to build one of those in a different way. So by focusing on the what that we want to build as opposed to the how it's built, it really allows us to be much more, to do a lot more, much smarter things and build in a much smarter way. So I'm going to give a quick demo on that stuff. So what I've got is I've got a really basic project. Gradle, a basic C++ project. We've got two, so there's a source directory. What I've done is I've put the sources in the conventional location where Gradle will look for them, so I don't have to configure the source locations. But here's my source for my hello world exe. There's my C++ file. you can see it's including a hello.h file, and it's calling the hello method on that. And then we have the say hello library, which has the hello.h file. Does a little bit of stuff, so it'll work on Windows as well, which doesn't matter right now. And there's my implementation. You can see the implementation right now has a macro which we'll use to show how we can configure how it was compiled. So let's look at my Gradle build file. So I've got I might even just comment out the library for now. So all we've got is an executable defined. We've got our native component plugin applied. We've got our C++ plugin applied, so we know we're going to build native components from C++. So now let's have a look at the first thing we'd want to do when we come into when we're building in the native space. A really useful tool is the components report. So I'm going to that's what I want to be. So I'm going to just run Gradle components. This is going to show us everything what we're planning to build, what this project is going to build. So this is one of the benefits of an explicit model, is I can say what components are there, how are they wired up. So for now, we can probably ignore the binaries section and just focus on this top. So we've got a native executable called hello world, and we have a bunch of source set. We've got a single source set. Its full name is hello world CPP, and that's where it's going to look for its sources in hello world CPP. So if I now go into add the native library, I'll do the same thing again. Scrolls off the screen, but you can see we've got the native executable and we have a native library defined. One thing that's interesting to note is straight away we have binaries defined for each of these components. So basically this is all the information about what we would build for the hello world executable. We'll build a single executable. It's got what task to use to build it, how we would install it, got the platform that it's built for, the build type, the flavor. I'll get into this stuff in a little bit. And then where the executable file is going to be generated. So it's a useful tool. When we look at the native library, you can see we're actually building two binaries, a shared library and a static library. So I mentioned earlier that the shared library and the static library are we consider them two variants of the same thing. So this session finished at 12:45, right? Does that make sense? Someone tell me if I'm wrong. I'm assuming that. Okay. So cool. Okay, cool.
So it says 12:30.
15 minutes. Okay. I'll try to get it done in that time. Okay, so that's the components report. So I'm going to try to build the hello world executable. And we get a failure. Can someone tell me why that failed? Why it didn't just work? Looking at the build script, what haven't we done? So we haven't declared any dependencies. So we haven't said that the hello world executable depends on the hello world library anywhere. We've got them both defined, but there's nowhere in my build script that says this hello world executable depends on that hello world library. So we're going to do that now. So what I'm going to do is say the C++, oh, that's the wrong one actually. C++ source, the sources, they depend on, say, hello. So now I've said that the hello world exe is dependent on the say hello library. Now if I try to build, you'll see what will happen is it'll build the library. So it's compiling. It can compile the executable fine and then it can compile the library. It can't link. It has to link the library. Then well, it doesn't have to. This task here doesn't actually do anything. It's the life cycle for all these. Then we can link the executable against the linked library and build the hello world executable. Finally, what I'm going to do is I'm going to install that because it's more interesting if I can actually run it. So if we look at what we've got produced, you can see I've got a hello world executable called hello world. I've got a shared library. That's what a shared library is called on the Mac. We're just looking here. And then we've got an install image which has a shell script and that bundles these things up and puts them in the right place. So if I just want to run that, I can just run build install hello world, and we've got it working. So what I'll do is just one little thing to show how we customize a native library. We're going to do we're going to basically say for every binary, every say hello binary we want to build, we want to define a macro. So we're going to do, so when we compile it, we're going to define the Australian macro. And what we'll do is we'll rebuild this and we'll run it. And what that macro has done, we see is saying g'day world now. It's because we've got in our source if def Australian, say that. So just showing how we can customize the way something's compiled within within a native component. Cool. So I want to quickly touch on variants, because all we've done so far is produced a single variant for the executable, and we've produced, without even trying, we produced a shared and a static library variant for the library, but nothing too interesting there. So the thing about variants is it's different outputs for the same component. So whether we want to do, there's a bunch of different ways that that variants can vary. So we've defined a bunch for the native space. We've already gone over linkage, which is basically a static versus a shared library. We have this concept of a build type. So a build type is what we consider a build type to be two things that are functionally equivalent, but different in non-functional ways. So debug and release, whether it has debug symbols or not, shouldn't make any difference to how this software works. Whether it's optimized or not in terms of a jar, or whether it's obfuscated or not, or whether the JavaScript is minified and compressed or not. Those things don't change the functionality that's there. So, but you can define like that. That's just how we imagine build types to be used. It's a fairly flexible set there. We have the idea of a platform, which is the runtime that you expect your artifact to be. So the runtime environment for your executable. So that's in the native space, we consider that to be the operating system and the architecture. I'll actually get into a little bit more later. And we have a concept of a flavor, which is basically a bucket that you can use to define differences between things, arbitrary differences between things. So a classic example in the Android space is a free versus a paid version of this application. But there's probably lots of different uses of flavor that you might want to use. Coming soon, not yet, but the plan is to make this set of variant dimensions flexible. So not only you currently can easily add a new type of build type or a new platform, but you can't add a new category to this. And the idea is that soon we're going to add the ability to add a new category, so you can have any number of dimensions of variants. So what Gradle does is it takes a component, it looks at the dimensions that apply to that component, and it defines the cross product of those as binaries. So if you have two of those, you've straight away got 8 possible variants to be built. You can restrict the subset to say, actually, I only want to build this particular component in release form, but by default, Gradle's just going to say, define the full set. Doesn't mean it'll build the full set, but it defines that full set. And as soon as you add 2 of these, and you've got linkage, I don't know, 16, 32 different libraries. So you can see it can explode pretty quickly, but the idea is that that Gradle will resolve the correct variants, and so you're not choosing which one to build each time. You're just choosing one entry point, and Gradle will resolve the right variants there. And I'll get into that in a little bit. So just how we define these things. So once again, they're inside a model block, similar to the components container. We have a build types container, and you can say add arbitrary number of build types to there. And a flavors container, you can add an arbitrary number of flavors. The default, we have a single default for these. Debug is the default build type, and default is the default flavor. If you define some, they override the canned ones, I guess you could call them. And so what we want to do is we want to actually customize based on these flags. So just by defining the variant dimensions doesn't do much, but they provide a place that we can go. We can add plugins that say, oh, I know how to build binary. I know how to build debug binaries. Okay, cool. So any debug binary, I know the right compiler flags to do. We can have some sort of convention or some sort of configuration that says I know how to build things for that flavor. So we can basically, out of the box, Gradle will just define the set of binaries, the set of variants. It's very easy for you in your build script to say to tell Gradle how to build them differently. Platforms is slightly different than the other two in that Gradle does have an inherent knowledge of what these things mean. So Gradle doesn't have an built-in knowledge of what debug and release mean to you. So you define what they mean. But we do have a built-in knowledge of what platforms mean because we need to use the toolchain in the correct way in order to build for those platforms. So there's a bunch of built-in operating systems and architectures that you can define, and you can combine those in arbitrary ways to define platforms, and then Gradle will build those variants for those platforms, just like any other variant dimension. But these values, the operating system and architecture values, are what Gradle uses to determine how to configure GCC to build for this particular, or whether GCC can build for that, or whether it's only Visual C++ can build for that platform. And so the platforms are fairly tightly tied to toolchains. And Gradle has, I talked about GCC, Clang, and Visual C++ as the built-in toolchains. What this is demonstrating is configuring those toolchains. So they're available by default. But if you need to tell Gradle, I need to use GCC from this path, or my Visual C++ is in a different directory, you can basically configure the set of toolchains that you want to use. And we want to make this a bit more powerful. We want to make this a bit more, we're not quite, like what would be nice is for you to say, I want GCC version 3 and for Gradle to locate it on the path. So rather than saying, here's the path to GCC, saying I want one that is version 3, you could do that with custom build scripting, right? You can go and look for it yourself, but Gradle's not yet there where it doesn't yet go, there's no syntax for you to tell us, just use version 3 and we'll locate it. We do look in the Windows registry for the Visual C++ installation, so you don't need to do this. It's possible to configure these things. So the way platforms and toolchains operate is, this is an ordered list of toolchains. Gradle gets a binary, a variant that has a particular platform. It goes through those toolchains, says, can you build a variant for this platform? If it says yes, Gradle says, cool, build this for me, please. If it says no, it goes to the next in the list. And just goes down. If it doesn't find any variant, any toolchain that can build for that platform, then that variant is considered unbuildable on that platform. So you can have, obviously on Windows, you might be able to build half of your platform, half of your variants, and on Linux you might be able to build the other half. So it'd be quite uncommon to be able to build all of your variants on the same machine. So So we then use the assemble task to say, just build me all the things that can be built on this machine. Okay, I'm going to give a quick demo of that stuff because it's kind of interesting. So I'm going to add a couple of build types. Actually, no, I'll add a flavor. That's probably more fun. So I'm going to add an Oz and a US flavor. And I'll just show what happens when what happens to the component. Oh, don't do that. What happens to the components report? So you can see now we're going to be building two executables, two variants of executables. One's the Oz one, and one's the US one. I think you can see where I'm going with this. At the moment, they're both going to be exactly the same. So I might do Gradle assemble, just so we can build all those things. And you'll see we're building a whole bunch of things. We're building the say hello shared library Oz version, the static library Oz version, the shared library Oz version, the hello world executable US version. We're building a lot of different variants. And if we look in here, we can see now we've built different variants of our binaries. just delete that directory because I want it to be clean. Okay. So I might just install those two. So what would be install US hello, that should work. And I'll install the Oz version as well. So now if I run one of those, oh no, my US version is speaking Australian. So what do we think we need to do about that? So so basically I'm saying for every binary, define this macro. So instead of saying that, what I can do now is I can say, actually, I want to do if the flavor equals Oz, then define that.
You don't want to say Oz instead of all.
No, that syntax is not. We will plan to add a more powerful matching syntax, but there isn't a syntax for that now. So now I'm going to have to build that again. So I'll just, so if I install, oops. So I've installed the US one, and now it should speak the right language. There you go. So we're done? Okay, cool. All right, guys. So the only thing I was going to talk about quickly was the model-aware dependency management. So this is something we've done in Gradle in native space so far. Is that we're basically allowing there's some complications involved in dependency management when you have binary variants, when you have multiple variants. And deeply baked in dependency management in Gradle has been this concept of I've resolved the module, therefore I know the artifact to use. So suddenly we need to resolve the variant dimensions, that we need to know about compatibility. And this is stuff we've worked on and we'll be getting better in the future. We need to resolve the actual type of the thing, so we need to know it's a shared library, so we can look at it as a library and get the header files from it. It's not always going to be a jar file that we get back. And we want to resolve based on context, which is how we're trying to use this thing. Are we trying to compile? Are we trying to debug? Are we trying to link? All these different ways we need to use in the native space that didn't come up in Java. So we've already built some model-aware dependency management, and we're working on making that much richer.
Is any of that available to play with now, or is it?
Well, so dependency management is available, and it matches. It does. So I just demonstrated that we had an Oz variant of the executable, and it depended on an Oz variant of the library, and that stuff works. So platform, it matches, but it matches there's a one-to-one match. There's no sort of flexible matching there, and also it's done in a way that we can't translate it to other domains. So it's very native specific, and we're building now a dependency management engine that can be generally applicable to variants in all domains.
Now, the stuff in your last talk about replacing, say, a project dependency with binary dependency.
Yeah.
And you mentioned that there was some of that coming from the native space.
Yeah, but it won't, because it's been built in a very custom way in the native space so far. So the plan is to make it more general. So I'm going to have to wind it up. So please come and chat with me anytime this week, and I'll be around. Sorry about rushing through that at the end. Thanks for coming.